Hey there, I'm going to open this up with a disclaimer. Check out the video in the description if you want to solve this problem yourself. However, I'm going to describe a novel formulation for it that I haven't seen anywhere else that maybe just requires a bit of intuition applied appropriately. So anyway, the problem in question is called the coin rolling paradox, where you have these two coins, say one with the radius of 3, one with a radius of 1, and you want to know that if coin A rolls around coin B, how many times does it have to rotate? How many times does coin A have to rotate to traverse this path? And my intuition, like I'm sure a lot of people was, to just relate the circumferences, which is incorrect. And a little bit of experimentation, you take 2 quarters, you'll see that this isn't the case. If you have, say, the same radius, that first quarter is going to have to rotate twice to get around it. So I'll show you actually how to derive that relationship pretty simply here. And it's a way that I haven't seen anyone else explain this effectively. So you have 2 coins, one with a larger radius, okay? And the way that this coin A is going to relate to the other coin is by sector, okay? So you should remember the relationship r theta as giving you a sector length, right? So that would be the total length that through an angle theta, A would roll through. And to that, you see I have my physics book up here. In physics, we actually write that ds dt equals r d theta dt, which tells you that the speed of the center of mass is equal to the radius times the rotational velocity, okay? So to relate that to this coin rolling problem, we write down the integral of this VCM and we relate it to kind of our known target, okay? So if this smaller coin rolls around, the center of mass is going to roll through a circumference that's the sum of these 2 radiuses, okay? So it's going to roll through 2 pi r hat plus r. And then on the right-hand side, we have this r omega. And then a little bit of derivation will give us r times the integral of d theta dt times dt. Those cancel. And now we know that this relationship relates directly to r times theta, okay? Where theta is the total amount that this small coin rolls through. So if we divide both sides by 2 pi, based on our circumference relationship, that gives us that turns theta into the number of revolutions, basically. And then if we divide both sides by the radius of the small coin, we get the answer that you see elsewhere. So that's kind of slightly better explanation, I think, of what's going on here. And you can see for our initial problem, where the larger radius is 3, the smaller radius is 1, we get the result that's expected.